Few things in this one, let's prove that square root of 2 is irrational, and the proof is basically, and by the way, irrational means it's a number that cannot be a real and it cannot be described as a fraction of integers. And so that means that square root of 2, if it's irrational, it's supposed to not be equal to some p over q, where the p and q are in integers and q is not zero. Q is not zero in the denominator, but p and q are integers. So fraction of two integers is a rational number and irrational if it cannot be described as such. So let's see. Let's try to prove it. Well, we'll try to prove it by contradicting the claim that it is a rational number. So if it's not a rational number, this initial assumption will be contradicted, and that will be the way the proof will go. And so here we see square root of 2, we set it equal to some p over q, where p and q are integers, and we assume that it's a rational number. We try to come to a contradiction. So if we continue with this claim, we get some manipulations of this equation, squaring both sides, and we soon arrive at something. And the most important thing in this proof will be we're waiting for a loop to appear that will cause a contradiction. And now it might be confusing because the one thing was forgotten to be said, and that is p and q's are supposed to have a greatest common divisor of 1. That's very important, so we must state that, by the way. This must be stated before we go on with the proof. P and q have a highest common divisor of 1. That means it's the most reduced form. When we have a fraction of two integers, the most reduced form is when we can no longer decrease the size of these two numbers for the fraction to be equivalent. So the p and q are minimized to their lowest integer option that they can be. That happens when their common divisor is 1. They have no common divisor higher than 1. So then that's a reduced form, and we want that. We want really these p and q not to be any integers, but let's make that more clear. We want their greatest common divisor to be 1. So if it's that minimized form of the fraction, the most reduced form, we have 2q squared equals p squared. And the whole proof now will just rely on us, first of all, using the equation to say, oh, this is even, this must be even, and repeating these claims and taking steps based on that, and also getting to a paradox in a second. So first of all, this equation implies that the left side must be even. It has a 2 in the multiplication chain, no matter what q is, as q will definitely be an integer anyway. So left side is divisible by 2, and therefore both sides must be divisible by 2, and therefore 2 divides the right side as well, and therefore 2 also divides p. Alright, in other words, p is also divisible by 2. Because if we have the square of a number divisible by even, alright, I mean, even means divisible by 2, so I interchange these two terms, but what I mean is the same thing. When you have a square of a number being even, then the square root of that is even as well. You can think about it from the perspective that any odd number to the second power will be odd, and there's even and odd integers. So the remaining numbers, when we have a square, its square root will be even. And so this should be the case. And so if 2 divides p, that means that we can further claim that p is equal to also something that's 2 times some number, other number. Let's use n. And so p is now 2n. We just say p is equal to n because by this equation we derive the conclusion that p is divisible by 2. So if p is divisible by 2, we must be able to write it as 2 times something, some integer, right? The n. I mean everything, all the letters, I mean integers behind those. So, okay, now I will change the equation to p being 2n. But we see we arrive at sort of a paradox by now, but we haven't gotten there quite yet. But we see now the equation looks basically the same, just we've switched one of the letters compared to before. Instead of this, we now have this. So it's different letters, but It's a very similar equation. But again, we keep doing the loop. If the right side is even, because there's a 2 in the multiplication chain, the product chain, the left side must be also divisible by 2. It's an equation. So q squared, so 2 divides q squared, therefore 2 divides q. That's an implication directly from that derived. And so q can be written as using some letter m, as 2m. Something's divisible by 2, we can divide it by the 2 and then m would be yielded, so that q is equal to 2m. So now again, 4m squared instead of q squared due to this. And on the other side, 2n squared. And reducing it is 2m squared equals n squared. And we got something that completely replaced both of the letters. Now there's neither p and nor q. Now it's m and n. And so now we re-express the form and we got new letters instead of the p and q. That means we replace that p and q also in the initial fraction by some m and n. And that means what we were doing here, we were sort of reducing it down to smaller numbers. And that contradicts the initial assumption that they were the smallest option, the most reduced form of the rational number expressed by a fraction. So the p and q weren't the smallest. And so thereby we contradict the claim that square root of 2 equals p over q. So here is the contradiction. 2m squared equals n squared. We now establish new letters that would replace the m and n, but p and q were supposed to have a greatest common divisor being 1. But now m and n would be at that place, but if p and q were that, then this couldn't have happened, but it did. We were following straight logical steps from the initial point, because in the beginning we had this square root of 2 equaling p over q. We squared it, we got the 2. And with that 2, we were getting expressions that were telling us things like the left side is even because it contains a 2, so it must be even if q is 1, or actually 0 is even as well. But we set q not to be 0, so at least it's 1. But whatever that is, well, left side is even, so right side is even, so p squared is even, but by number theory, or thinking about it a bit, we realize, oh, square is even, then the origin number is even. So p was even, and p as an even number, as any even number, can be expressed by as 2 times whatever's left when it's divided by 2. And so that n was, of course, an integer again. We put it back in the equation, we get this. But then we get to a very similar scenario. This looks very similar to this initial equation. And we see we start replacing these letters. Gradually we repeat the process. We also find out that we can say that q is 2 times something. By the way, of course, an integer, meant as such all along. And so we have 2m squared equals n squared now, instead of 2q squared equals p squared. Well, we got there by considering what is supposed to be even, based on how the equation began from the beginning. But we only got to m and n, replacing p and q as those that are supposed to have the greatest common divisor 1 in that supposedly most reduced fraction, because the initial assumption was wrong and therefore is contradicted thereby. So that's how we arrived at the contradiction. Alright, so the greatest common divisor of p and q actually wasn't 1, because if it was, we couldn't reduce it further. And so there we go. We assumed it's a rational number, we got the contradiction, so it's not rational, right? So we did by contradiction, and yeah, the way we got there is we went into this loop. And you can also see that we can infinitely continue this loop. As the similar way we viewed it. All we did is, so one side is divisible by 2 because it obviously contains a 2. Other side must be also, equation property says that. And then, if something is divisible by 2, it must be expressible as 2 times something smaller than itself. Unless it was 0, of course, but anyway, we went in this loop, we got here, we could repeat it furthermore, you know. taking new and new letters by this logic. So, and that loop wouldn't happen if we were stopped by the fact that P and Q cannot be reduced. But because we assumed wrongly that it's rational, we could keep going in that loop. And that brings one to that contradiction.